This is 2.3 Fatigue and Recovery, and this is the recovery process. I've talked about the things that fatigue us, and now I'm going to talk about recovery. Recovery is a phase when our body removes waste products and resynthesizes ATP, so that our bodies will be able to keep going and use the energy again. Recovery is all about the restoration, resynthesis and repair. This could be minutes or days, especially for repair. Each exercise has different demands on our body, therefore has different recovery. For example, a 100-meter will mainly be anaerobic and therefore use the PC system and may go into the lactic acid system depending on how fast they're running. They will not go into the aerobic system, and whereas on the other hand an 800-meter runner will use all three energy systems, and the marathon runner will predominantly be using the aerobic system. This is a recovery system, therefore recovery will be taking place while the athlete is running. Depending on the intensity and the duration of the exercise will depend on the recovery for the exercise. If the intensity is higher, there will be a longer recovery. If it's lower, the intensity and the recovery will be quicker. EPOC stands for excess post-exercise oxygen consumption. These graphs show submaximal and maximal EPOC graphs. The submaximal shows a steady state, which is a plateau on the graph. The shaded areas show oxygen deficit. This is a temporary shortness of oxygen during exercise. If our bodies were perfect, then the exercise graph would go straight up, straight across and straight down. However, because we do not have a perfect body system, we have to recover what oxygen we've used up. In submaximal there will be a plateau. This is because there's enough VO2 required for the intensity of the exercise, for example a marathon run. If the oxygen deficit will be less, at submaximal, as the system is aerobic, so therefore they'll be using oxygen while they're exercising. Therefore ATP will be resynthesized constantly. The shaded area on both of the graphs is EPOC. The alactic phase is helping in recovering ATP and PT. It's the amount of oxygen taken on in recovery to stick the PC and the ATP back together. EPOC is where we recover and remove waste products, and it resynthesizes our ATP. Different intensity demands result in different amounts of oxygen deficit. Therefore, the larger the EPOC, as you need to recover more and get more oxygen back in. In maximal, you'll have a longer recovery and a larger oxygen deficit as you're working anaerobically. Therefore, there's a large amount of oxygen that needs to be recovered. The lactic acid phase of EPOC is removing excess lactic acids built up during exercise. So excess oxygen that is consumed in recovery will help remove the waste products from our body. As you can see, different exercises have different demands on our body systems. Therefore, if you're doing a 100-meter sprint, then your EPOC will be bigger as you need to recover more oxygen after exercise. Whereas in a marathon, because it's aerobic, you're able to get enough oxygen in, and therefore you don't have such a big recovery as you don't need to consume as much oxygen at the end to help remove the waste products. Now I'm going to talk about the slow components of recovery, which is the replacement of glycogen, the removal of lactic acid, and the removal of carbon dioxide. The first one I'm going to talk about is carbon dioxide removal. Carbon dioxide is a waste product of aerobic exercise. Carbon dioxide removes as carbaminohemoglobin, that's 23%. Little of carbon dioxide is removed in the blood plasma, so that's about 3%. And most of it is removed as carbonic acid, that's around 70%. Some of it stays in your body as you need carbon to be able to perform bodily functions. To be able to remove the carbon dioxide from the body, the cardiac output, which is the amount of blood pumped out of your heart per minute, must become bigger, as the higher the cardiac output is, the quicker you get rid of your waste products. So this is reliant on the cardiovascular system. Moreover, an increase in ventilation, which is the amount of times you breathe in and out per minute, will increase in exercise and recovery. As the higher the resting levels, then more carbon dioxide is breathed out. For example, in a netball match. If the muscles have a higher demand for oxygen, it means that cardiac output has to increase to pump the blood around the working muscles. As the muscles are working, they are producing more waste products that need to be removed. Therefore, carbon dioxide is breathed out. Moreover, once we finish exercise, the ventilation and cardiac output will stay the same, and it will stay above resting levels to help remove carbon dioxide, as too much CO2 will be increased, which means that acidity levels of the blood will be increased. Therefore, if it increases too much, the enzymes won't be able to work, as they won't have optimum conditions to work in, and they'll become denatured. Now I'm going to talk about the removal of lactic acid. The lactic acid system comes in after around 10 seconds of exercise, for example doing a 400-meter run. The athletes are working at high intensity and will build up a lot of lactic acid. It will on average take around an hour to recover this lactic acid. Roughly 65% of lactic acid is converted back to pyruvate acid, which then enters into the Krebs cycle, which produces carbon dioxide and water. It becomes an energy source again when there is enough oxygen available, or when there's not enough oxygen available, it becomes lactic acid. Around 5% is converted into glucose and around 20% to glycogen. 10% is lactic acid converted to protein. The photo above shows the Cori cycle. This shows making and breaking happening at the same time but in different cells. In the muscle, anaerobic glycolysis is taking place. This is where glycogens are being converted to pyruvate and pyruvate is converted into lactic acid, as there's not enough oxygen present. Lactate is then taken to the liver to be reoxidized to pyruvate. Glyconeogenesis takes place in the liver to make glucose. The glucose then goes into the blood, then goes back to the muscles for glycolysis. It's important that lactic acid is removed, as it can be a fatiguing factor to the muscles. However, studies have shown that it's the hydrogen produced when lactic acid is broken down that's the fatiguing factor, not the lactic acid itself. Now I'm going to talk about the replacement of glycogen. The form stored of glycogen is carbohydrate. There is more fat than glycogen, therefore glycogen stores are depleted quickly. As you can see by the graph, it takes a couple of hours to deplete your glycogen stores, and after this, it takes around 2 days to recover. If an individual was running the 100-meter, it's a short duration and a high intensity, therefore glycogen will be restored around 2 hours. However, if an athlete is running a marathon, which is a long distance and a long duration, it will take around days to be restored. Depending on the time and depending on the depletion will depend on the restoration. Things that will help restore glycogen is having a high carb diet, also known as carb loading. This is eating a big carb meal the night before a race. First 2 hours before a training session, you should have something high in carbs, and during the training session, the individual should take supplements to keep them going and to keep their glycogen stores high. For example, while running a marathon, the first few hours will be fine, and the athlete will need to keep running. However, after this, they will need to take supplements to keep their glycogen stores high enough. After training, to achieve a good recovery, around 300–400 calories of carbohydrates should be consumed. And another 2 hours on, the individual should take another 300–400 calories. Metabolic needs is an extra CO2 consumption after exercise by organs, for example the heart and the respiratory muscles. The heart muscles will need an increase in oxygen, and so will the respiratory muscles as a result of exercise. Now moving on to recovery, the active cool down, which is the muscle pump. A recovery gets everything back to normal, for example, cardiac output, ventilation and temperature. Recovery is dependent on the demands of the exercise. For example, a marathon will have a much different recovery to a 100-meter sprint. It's important to have an active cool down, as this is to stop blood pooling and to help prevent DOMS, which is delayed onset muscle soreness. The skeletal muscle pump will help keep blood flowing if an athlete keeps walking after their event. It will help keep the muscles in our body contracting and having constant contractions, so this helps the blood keep flowing and keep moving around our body. Studies tell us an active recovery after an event encourages the recovery and reduces muscle lactate levels. This was suggested by Ahmed et al. 1996. Other studies show us that active recovery did not decrease in active physical recovery, but it had a positive effect on their psychological effects. Moreover, low-intensity active recovery appears to significantly reduce the accumulation of blood lactate and speed muscle recovery in increasing blood circulation. However, recovery is also based on your general level of fitness. As you can see by this graph, fitter individuals will have a much quicker recovery time, as their cardiac output is better than an unfit person. To get a better recovery, an individual will need to increase the quality and intensity of their training and improve their energy system adaptation. Once again, this could be done by improving their training schedule. Other strategies to recover is cryotherapy. This is using cold substances like a cold drink, an ice bath, or even an ice jacket to help aid in your recovery. Another way is a sports massage or even changing an individual's diet to cut out the saturated fat, which can cause fatty deposits to build up and prevent contractions of the heart, so less blood will be able to get out.